Good afternoon, everybody, both online and physically present. Can you hear me better now? Okay. Thank you all for being here to this EURECA-PRO lecture. So I would like to introduce to you Professor Adam Długosz, who is from the Department of Computational Mechanics and Engineering, the Faculty of Mechanical Engineering at the Silesian University of Technology in Gliwice, Poland, correct? Right? So the SUT is a partner of the TUC within the European University EURECA-PRO. This is why this is an invited EURECA-PRO lecture. So Professor Długosz here is visiting us this week. What he's going to talk to us about today are some selected aspects of multicriteria optimization problems in mechanical engineering using metaheuristic algorithms. And before giving him the opportunity to talk to us about his interests, let me just say that he primarily works with multicriteria optimization, metaheuristic optimization methods, numerical modeling of coupled systems, and applications of CAE systems in identification and optimization tasks. Now, last but not least, you will find right at the exit of this room, for the people who are present here, a QR code. I invite you all, please scan the QR code and fill in a very brief questionnaire about your attendance. And you will also receive a certificate of attending this lecture. Equivalently, for the people who are watching this lecture online, you will be able to fill in the equivalent form online through a link in the chat. So without further ado, Professor, welcome.
Thank you so much.
And please, the floor is yours.
Yeah, thank you.
You're very welcome.
Okay. First of all, good afternoon. First of all, I would like to express my thanks to inviting me here, to giving an opportunity to visit your university. Special thanks to Dr. Nicolas Dianaklestis. Thank you so much. Many thanks for a nice introduction. So the topic is here, so I didn't read again. I work at the Silesian University of Technology at Gliwice. This is the southern part. This is located, a medium-sized city in the southern part of Poland called Silesia. Majority of our faculties are located at Gliwice. Some of them are located in Zabrze and Katowice. So our university consists of 13 faculties. Our faculty consists of 8 departments. I work at the Department of Computational Mechanics and Engineering, which is not quite a big department, less than 30 people. Our activity and research interest seems to be very broad, but we are mainly concentrate on simulating different physical fields using different numerical methods like finite element method, boundary element method, finite difference method. We are focusing not only on solid mechanics, but also some aspects in transfer problems and also biomechanical engineering. Some of us deals with methods of artificial intelligence like artificial neural network, or like me, genetic evolutionary algorithms. So this is connected with optimization as the topic of on my presentation. More information can be found on our website. And my scientific activity focus on such problems. Dr. Dianaklestis told about it, so I skip it. So now I'm going to go to my lecture. If we want to talk about optimization, let me remind that optimization can be defined as a process of finding a possible best solution. In practical cases, sometimes it's not. Sometimes we cannot obtain the exact solution. in real engineering problems. So the main goal can be state as an improvement. If we can improve some aspects of a real engineering problem, we should be happy. There are many different categories of optimization methods. This is one of the possible, that we can divide it into the analytical, and numerical, and stochastic method. The highlighted is bio-inspired algorithms. Why? In case of multi-criteria optimization, such algorithm, which not only bio-inspired, the broader, wider class of algorithms called metaheuristic, because they have some stochastic information, some randomness in the, not like analytical, which are deterministic methods. Why such algorithms are interested or useful in multi-objective optimization? Because in every iteration, they process not single solution, but a set of solutions. So in the concept of Pareto, which I'll be talking later, this is a ideal candidate for such technique to optimize. So over the 30 years, there appears many different types of algorithms. This bolded maybe are more popular. So genetic evolutionary algorithm, maybe particle swarm optimization. Probably you heard about type of algorithms or like artificial immune system. Many of these algorithms have also version of a multi-criteria optimization, not only for the single objective optimization. Another advantage and another feature of meta-heuristic algorithms is the ability to avoid a local minima. Because of the randomness and because of the strength that they are working on the set of individuals or set of solutions, they exchange some information, so they able to omit some or getting stuck in the local optima. In the case of analytical method, based on gradient or non-gradient optimization, usually we have to choose the starting point, and after that we seeking for the direction of improvement, so we may get stuck into the local optima. In the case of real engineering problems, it's very important because many problems are so difficult, have multimodal functions, so there exists a huge number of local minima. So this is the reason why we use in many cases heuristic algorithms. In the case of multi-objective optimization, we deal with not one objective, but more, 2, 3, or higher number. Usually in the real world engineering problems, the objectives are contradictory. So if we want to increase some objective, we have to decrease another one. So the result of optimization is not a one single solution, but a set of solutions, which is called optimal, but in the Pareto sense. So like on this figure, this is examples. So we can define the multi-objective optimization, like on this slide, this is the process of finding a vector of design variables, X, which minimize or maximize not one, but the set of objectives. In these objectives, it may be include some constraints. The constraints may have form inequality or quality constraints, and usually on each design variables, also box constraints are imposed. There are many different methods to solve such problems. We may use some called a priori methods. First of all, we have to define some assumption, make some assumption before optimization, and therefore perform the optimization and obtain solution. Another way is not giving some assumption before optimization, but use a Pareto concept. We have to modify the algorithms of optimization. And as I said, in this case, we obtain not a single solution, but a set of solutions in the Pareto sense. So it may be represent like this. So the green line is we have to introduce some information, some parameters, and we may use algorithms which is also used in the single objective optimization problem, and we obtain one solution. Another path, we have to modify the algorithm, we obtain the set of solution, and after some information, we may choose the one or a few solutions. There are many different types of traditional methods. I will only mention about two of them. The first is the weighting sum method. So this is some kind of scalarization of the problem. If we have more objectives, 2, 3, 4, and more, we may use such formula where for each objective we have a weight. And this is a sum of multiplying weight, function, weight, function, weight, function, and so on. So this is the way of transforming the problem from the multi-dimensional objective space into the single objective space. But the problem is how to select the weights. And another problem is that if we select the weights, we obtain only one solution. But the advantage is we may use algorithms which is popular in the single objective optimization. Another problem with this method is this is a linear combination. So if we have a non-convex Pareto front, we cannot obtain a solution for such cases, and this is very common case in a real engineering problem. Another method called epsilon constraint. So this trick in this method relies on that we choose arbitrarily one criterion and other criteria plays roles as a constraint. So this works like a threshold, yeah? Another criteria, we give some values for the other criteria, but such methods have also disadvantages, like how to appropriately choose this threshold, and also one run of the algorithm, one solution. Okay, back to the metaheuristic. Due to the 30 years where researchers developed many methods which are mainly based on the genetic or evolutionary algorithms like this. I said why, because it's a population-based algorithm, and they based on the Pareto concept. Some few words about the Pareto concept for the people who are not familiar with this. If we consider a minimization of the problem, so if you want to minimize, for example, only two functions, so we have a pure objective optimization. So if you want to minimize F1 and F2, and let's consider let's consider only the solution F. So the solution F dominates the whole solution is this shadowed region. So every solution is in this region is dominated by F because both functions are better with respect if we consider minimization. We may talk about strong dominance and weak dominance. Weak dominance is if the solution, if we compare the solution and the solution lies on the curves of this region. We have some terminology of the Pareto dominance, and this non-dominated solution creates fronts. Yeah, this non-dominated solution create fronts. This is the blue dots. The yellow dots are dominated solution. If we deal with two objectives, this is the result is a curve. If we deal with three objectives, it's a surface. If we deal with four objectives, we have problem. But in many practical cases, we deal with five and more. And I will show some tricks how to deal with this problem. So summarizing, I think the blue path is a better way, not only from these features I called, also if we run algorithm once, we obtain the set of solution. We have another advantage. We obtain the front. The front may have a different shape, and the shape also gives us an information of the problem. If some region of the fronts are, for example, very sticky, you may not change so much one criterion, it influence another criterion. So this information also can be useful for engineers. So this animation is an example of optimization. This is the population. The animation, each frame consists of a set of solutions from the genetic optimization. And if you see the first frames, the solutions are dominated and not dominated. And if the process going on, the solution are pushed to the ideal utopian point. This is the cross of this axis. It's impossible to obtain this region, but you see how it can we visualize for the genetic optimization. So if we zoom it, you might see how the Pareto front looks like. In multi-objective optimization, we have also a problem with local minima. So apart from the global Pareto front, we may obtain some local front. So in the solution space, we may see that some fronts are closer to the utopian pole, or the distance is longer. Okay, if we modify algorithm for the single objective optimization problem, new algorithm or well-known algorithm, it's good to fulfill some requirements. So here is the list of the requirements. Maybe I mention only about the last one, because it is good that user don't have to manipulate any additional parameters apart from the known parameters typical for example, genetic algorithm or particle swarm optimizer. So this population size, the probabilities of operators, we have to specify, but not other. It's good. I don't know if you heard about this NSGA2 or SPA2. This is maybe the most popular algorithm for the multi-objective optimization based on the evolutionary methods. I suspect that most of you uses MATLAB software. If you uses Optim tool library, this is included as well. From my discipline, many CAE software also have embedded NSGA2. So this is very popular algorithm, not in mechanical, but in chemical and other engineering disciplines. And I will show you our research, which is I'm talking about NSGA2 because our proposal is uses some mechanisms from the NSGA2, but with some improvements and modification. And I don't know what is. Here should be a scheme of my algorithm, but never mind. I don't want to go into the details. How precise how precise it works. The algorithm, as I said, has some similarities to NSGA2, but the improvements is in the selection mechanism and in the operator. Okay, never mind. This is a typical scheme of the working, but I'm not going into the details, so never mind. If we want to compare algorithms, new algorithms, and if we want to be fair, we have to use some matrices which can measure performance of the algorithm. If we deal with a single objective problem, this is not such big problem because if we minimize the function, then lower value is better. Yeah, if we maximize function, the higher value is better. But if we deal with multi-objective optimization, not only the closeness to the true Pareto front is this is not only the one thing. The another thing is that we want to obtain as much as possible uniformly distributed solution on the front. We don't want to. We have to omit situation that this front do not cover whole the searching space. And another feature, we want to cover the front as extent as possible. So we have a free feature, like here, closeness, distribution, so uniform distribution. This is the spread of the front and uniformly distributed. There are different matrices to measure such feature. Some matrices measure the closeness to the Pareto optimal front. Some matrices measure the distribution. Some combining it, and very popular is hypervolume indicator, which measures all three features. And we compare our proposal to NSGA2 on the set of objective functions. Some functions are simpler, some are more difficult to optimize. We choose not only a not constraint optimization, but also the case where for the objective also constraints are imposed. This is also very practical case where you cannot obtain solution when you manipulate design variables. For example, you have empty, and you have no solution. So it's necessary to check it. This is the shape of this function. Maybe not looks very interested, but some of them, as you see, are not convex from. Some have discontinuous, which is difficult for optimization. Some of them, for example, before, have a huge number of local fronts. As I mentioned, from the practical point of view, we should have an algorithm which can skip and run from local minimum. And this is the visualization of the constraint optimization and the results. The results in table, the algorithms are better, not for every case, of course, but it's better, especially for the function which are more difficult to optimize.
For example, as I mentioned, with a huge number of local minima. And here is one example, the comparison between NSGA2 and our mock-team algorithm. For this function in whole objective space, there are a huge number of local Pareto fronts, and we done it. Here is the information: 30 independent run Bob algorithms with 100 population size and 2,500 iteration. So this is the result. If we prepare a visualization of the results of the Pareto front, you can see that NSGA2 may stack in the local solution, not like NSGA2. If we want to solve if we want to solve real-world optimization problem from my discipline, mechanical problem, we have to combine the algorithm with a proper code. It may be commercial, or it may be your own code written, for example, in MATLAB, which simulate the physical problem. In many cases, the simulation are based on finite element method, because the finite element method is maybe the most popular. Apart from boundary element method, finite difference method, or some meshless method, we have. It looks like a puzzles, but you have to deal with a proper interface. It's usually done through files. So if we deal with evolutionary method, genetic or evolutionary method, every solution is represented by chromosome. Chromosome consists genes. Genes codes the design variables. So on the chromosomes genes, you have to decode the design variables, build a proper boundary value problem, and after you solve your physical problem, on the base of the results, you have to read these results and calculate your functionals. So the loop may look like this. So this is a loop. Typically for the finite element method, you have to first create geometry, you have to generate mesh, apply boundary conditions, apply other aspects of analysis, solve the boundary problem, read results. So the loop looks like this. Why numerical simulation? Maybe for some cases you may use analytical formula, but probably you know analytical formula are limited only for the case which are simple. For example, beam, we have analytical formula, but this is only the case. If we have a more complicated object, not only from the geometrical point of view, but material properties, boundary conditions, or non-linearity in the system, we have to use some numerical simulation. Generally, finite element method allows for us for transform the continuous partial differential equation into the approximate solution. We introduce the elements, nodes, and elements, and this is example the equation for the linear elasticity called the Navier-Cauchy equation, which is written in the tensor form, may be transformed into the algebraic equation, which is usually written in the matrix formula. And this is, after that, by applying boundary conditions and some other introducing shape functions, we may solve the physical problem. This is not only typical for the mechanical, from mechanical point of view. Electricity, heat transfer problems, acoustics, and so on. Many different physical problems. In finite element method, we deal with 1D elements. Here is examples. It's rods, beams, frames, like on this figure. 2D elements. This is the thin shells, modeling the shape like this, and of course 3D elements. And I present here maybe 4 examples of reading CA. CA stands for Computer Aided Engineering. So this is the software which are utilize the finite element method. And if you want to prepare a system like puzzles, which was presented before, you have to go in deeper into the system. Usually this system consists of pre and post processor. This is a program with a graphical user interface when you may create your geometry, finite element mesh, and so on. And the solver. Solver only solves the problem using finite element method. And this pre and post processor means that after the solving the problem, you may make some graphs or colorful maps and prepare reports and so on. So every system, almost every system, have included the specific language, which is some kind of script, and allows for automatic generation of our boundary value problem. So I only show this one example using the one selected software. The scripts looks very simple. There are comments which are responsible for creation the geometry, some transformation, mesh, some introducing other features like materials, geometrical properties, boundary condition, and so on. But if we want to use this software, not typically by invoking the graphical user interface, it's better, or we have to invoke it into the background mode. So if we want to create the system like I present, majority of systems have the possibility to invoke it in the background mode. Since there is some parameters, you may invoke the preprocessor in the background mode and the solver. So it's good to not invoking the whole graphical interface. After solving the problem, when the system writes down the results file, you have to create your own procedures to read the results and to formulate before, but after implement and calculate the objective function. So after that, you may create the system like I present. Sometimes in geometry modeling, we are used some parametric curves. It is very useful if we deal with shape optimization problem, because we can generate some smooth shapes. We can not rely responsible on the coordinate of the nodes, but manipulating the position of the control points, we may produce a smooth boundaries, and also we can reduce the total number of design parameters. And not only Bezier curves, but also some splines or NURBS can be used in such case. And the first example is with the cooperation of Flytronic company. This company produces drones, not among others, UAV, unmanned area vehicle, and the wing of the UAV may look like this. You may see that it consists of 3 different materials. This is the cross section of the wing. And first of all, we check. We perform the experiment to calculate the stiffness in order to validate the model. after the validation of the model, this is a very simplification, because in this work we used 2D model, but after that this model was extended, and also the three-dimensional model also was considered. So after validation of the model, we obtained such numerical model like presented in this figure. We solved the problem of linear elastic constitutive model for laminates. And very quick and very short, what was the idea of this optimization task? If we change the geometry, external geometry, we have to deal with calculation of aerodynamics, because we change the airfoil. So our idea is not to change the external surface, but we want to improve the mechanical properties, but manipulating the internal parts of this wing. So we parameterize this task. As you can see, some design variables are responsible for the position of the girder, or thickness of this girder, or length of the roving, and so on. And we define 3 objectives: minimization of the mass, minimization of the stresses. The stresses is calculated as equivalent stresses. For Mises, this is one of the hypotheses. And maximize stiffness, which is more or less the same as a minimization of the displacement. And we solve the problem taking into account two of these objectives. So each pair, first, second, third, sorry, or simultaneously optimizing all of them. So here is the example result of the optimization, B optimization. As you see, the existing design. So our set of solution dominates this solution. So we obtain some improvement. And here is the results of the optimization if we take into account all 3 functionals. A, B, and C represents the solution for extreme value of each objective, and D is a compromise solution. And this is also collected in this table. And if we focus for a while for the D solution, the D solution also has a lower value for each objective. And this is also here I present the colorful maps of resultant displacement and the equivalent stresses for this point D, which can we improve the solution. And the last part of my talk will be devoted to the case when the number of objectives is higher. In the context of multi-criteria optimization, higher means 3 and more. There are some problems and difficulties with solving such problem. As I said before, if we have 4, we have problem to visualize, right? But the 4 may be represent like this, that we have a surface, and the fourth objective can be represented as a color with a legend. So, okay, it's possible. But if we increase to 5 objectives, we have problem. Another problem, very big problem for a population-based algorithm is the fact that if we increase the number of objectives, for example, 4 and more, it occurs that whole population are non-dominated. As you can see before, we have 100 size of the population. You may extend this to 500 and so on, but it definitely be more time consuming. So we are searching for the solution for such algorithm which we not rely only on the improvement which is connected with the Pareto dominance, because there is no reason, there is no Pareto dominance, because all or majority of the solution are not dominated. So there is no drive to push the every iteration to the proper direction. The proposal is to combine differential evolution. Differential evolution is maybe, I might say, more or less the same as the genetic or evolutionary algorithm, but have some advantages comparing to this, like say self-adaptation and so on, with elements of game theory. And I have no so much time to going into details. This problem was solved within the PhD thesis under my supervision. And this algorithm called DAGT-DECT. Maybe I skipped this. This is the flowchart of this algorithm. And again, this algorithm, before we use it for optimization for mechanical problems, first of all, we have checked how it works with known algorithms from other algorithms for higher number of objectives. This benchmark mathematical test functions are much difficult to the previous one, because the higher dimensionality, and some of them are degraded from and so on. Let's summarize. This algorithm is not better for all cases, of course, but for some cases it's definitely better than NSGA2, because NSGA2 has the mechanism which are described. So there is no the drive, because the whole population for higher number are non-dominated. But NSGA2 is also have a consecutive version, NSGA3, and our proposal is comparable. For some cases is better, and it was also tested for the some benchmarks, mechanical benchmark, I will show you later. But there is another advantage, another fact. If we consider, for example, numerical simulation by finite element method, sometimes it's very consuming, because you may have a very complicated numerical model. And like previously, sometimes you calculate cost, area, mass. This is not needed to invoke the numerical simulation. It can be calculated in the easiest way. So some of the objectives can be time consuming, some not. If you use the algorithms like NSGA2, you have to calculate all functions for each individual. So it takes time. It may take time. In such a case, the player from the elements of game theory are responsible only for the one object. So for the objective which are not needed numerical simulation, or numerical simulation sometimes is more consuming or less consuming, you may do it more iteration and you get it faster, and so it's more efficient to the traditional. This is another aspect of DECT algorithm. What about the visualization? The visualization, as I said, this is a problem. This is a problem. There are many different proposals for objective, as you see. Sometimes some researchers use a parallel plotting method, but it is not useful when you have a large size of the Pareto optimal plot. Some use a scatter plot, but scatter plot is some kind of projection of the multi-dimensional space into the 2D. So choosing the optimal solution relies on comparison. You have to compare or charts which are projection to the 2D. We propose and we use self-organizing map. This is a type of the artificial neural network called coherence network. And the results of working such network, the network produces the colorful map. Maybe I going into details and show you the last example, and maybe maybe better understand how to use it and how it works. DECT was also was used for solving engineering problems, as you see, with high number of objectives to test how it works. And the last example is optimization of the micro actuator. I don't know if you heard about it. This is a very small part in micrometer. The length is micrometer. There are different types of the micro actuators. The electrothermal works like this. You impose by a different voltage. This is made from polystyrene silicon, which has high resistivity. If you close the circuit, the current flows through the device. Due to the high resistivity, the high temperature refuse. In the high temperature refuse, the beams are extended. The extension of the beam pushes the central shaft. So it works very precise. The temperature are very high, but it works very precise, and it's very useful for some MEMS structures like microscopes and many other devices. So this is not a new. Some researchers also deals with shape optimization of such structures. Here is an example paper. And we define the criteria. Okay, here is 6 criteria, but I want to mention that naturally here appears more criteria because this is the couplet field problems. If we solve this problem, we have to deal with 3 different simulations: electrical field, thermal field, and mechanical field. So naturally appears more criteria, more restriction, more criteria. So our proposal was definition of the following 6 functions: volume, stresses, as in the previous example, not minimization, but we want to maximize the deflection, minimize the total heat generated by the actuator, maximization of the buckling factor. Thin when you bend the linear. I don't know, everybody knows what is buckling. Buckling is a phenomenon of stability. Yeah. So buckling factor is factor which which is responsible for safe from buckling feature. Okay, more or less, and maximization of the force generated by the actuator. So we have 6 objectives. So high number of objectives. This is the equation for the finite element method which have to be solved. And as I said, we combine it with a DECT algorithm. So sometimes not all these equations are involved. If we want to use bucket analysis, only this analysis was involved. If other. So here is the scheme of the problem of coupling DECT with a block of the FEM computation. Parameterization. We use parametric curve to model the shape of the beam. Model only the pair. You see that there's the list of pair, but if you manufacture this device, you may multiply these shapes. So if you increase some feature, some objective for the one pair, it should work for more complicated shape as well. So you see that the shape may be modified, and also some radius. Why radius? Because there's narrow, sharp edges concentrate stresses. So it also naturally appears. So here is the results of the optimization as a projection, a scatter plot matrix. Here is the results for extreme solution, and how to use the cohomon maps to visualize the plot. We have 6 objectives. So this nets produce the 6 colorful maps. So this is the objective F1, F2, F2, F3. Here is the legend. So it's the limits of the objective, yeah? The lowest value and the highest value. So, for example, let me remind what is the objective. The first is volume, the second is stresses, the third is deflection, and so on. It's also needed for me because we start from F2, yeah? We start from F2. F2 is stresses, okay? Okay, so let's start from stress. We see that we assume that the safe is for the polycrystalline silicon is that the stresses are not bigger than 1 gigapascal, for example. So we have to get rid of the solution which are higher than 1 gigapascal. So this is the region. Okay. After that, we may move it or transform to the another criterion. For example, let's move to the criterion which is responsible for the stability, for buckling. For buckling, let's assume that the safety factor, the threshold about 2. So our area is smaller, yeah? For example, like this. Next, we move to the another criterion. For example, responsible for the displacement. Yeah, we want to maximize displacement. So within this region, we are searching higher value, so more orange, less yellow. This is this region, and we may do that for the rest of the objectives, or quicker to check only transform this region with shape to other criterion and check. I accepted yes or no. I accepted yes or no. I accepted yes or no. And solution from this region looks like this, quite similar to this shapes which were obtained by other researchers. So this short but explanation how to use how to deal with multi-dimensional Pareto front. That's all. Thank you so much for this. If you have any questions, so I will try to.
Thank you very much for the presentation. Let's start with questions from the people online.
Okay.
Okay. We can have questions from people online first, and then we can move on to questions from the audience as well. Okay.
Okay.
So that's why I came up here, just to facilitate. Okay, great. So for the people who are actually in Zoom, are there any questions that you would like to ask? I don't see any questions from people online. So I will ask the exact same question to people present here. Any questions from the audience?
Yes. Game theory. It was. It's hard to talk in a few words. It was proposed by John Nash. Maybe you see the movie, the famous movie. Nicholas, help me. What was the name of the movie?
Beautiful Mind.
Yeah, Beautiful Line. Yeah, and it was he was the author of the theory and was famous in the economy. But the game theory also has some implication in other disciplines. So our idea is not revolutionary new because the elements of game theory also exist in the fields like this. Maybe I cannot explain it in a few minutes. You have players. The players may compete to each other, and in our algorithm, the players are one player is responsible for one objective. So it's a game. This game produce or moves this solution on the Pareto front. So I cannot explain it to a few else. Okay, if you can help me, so
very simply. Imagine that you are playing a game of chess. Okay, so what is the objective of player one? Conquer the king of the other player as fast as possible and preventing your king to being taken, correct? The other player has the exact same objective, but for himself, for themselves. Do you see what I'm saying? So one player makes a move towards their optimal goal. The other player will make then a move towards their optimal goal, correct? But from your perspective of player one, you need to consider what the next player, the other player, is going to do that is optimal for them. You see the contradiction here, the contradictory objectives. This is
the perfect explanation, and what this contradiction is the essence of the aspect of Pareto optimization. So this is the reason why we use it.
Any other questions?
Thanks for the interesting talk. For the sum-weighted method that you mentioned,
yes.
How do you choose the weights, the W and W? Is there any way, or it's
dependent on decision maker.
Yeah,
you may set
okay.
it 0.2, 0.8, and if you want to obtain the Pareto front, you may do it consecutive times and changing the weights constantly, and so there is no question.
Okay.
Sometimes I see some researchers agree and fine with selection. I prefer this criterion more than this, so I choose.
So you give priority to a certain criteria.
Solve only one problem, and it is better than existing. It's okay. It's okay.
What is the main reason of not getting a uniform distribution? I mean, Pareto front. Is that the constraints or the number of objectives?
Some Pareto fronts are discontinued as a nature.
Yeah, that's yeah.
But as a user, you want to see how the Pareto fronts looks like in the whole objective space.
Exactly.
So you don't want to see only the group of grouped solution.
Yes.
So the question is how do
you can? What is the main reason of having a uniform Pareto front?
This is the reason that you want to present the visualization of the whole Pareto front, if it's possible.
And the problems that you saw as the applications, how many nodes did you have in the numeric?
For the test was 100, and for application it depends. Sometimes 50, sometimes 100. It's quite big. Taking into account the numerical simulation, it's very time consuming. Sometimes it's less. For example, if you do non-linearities or dynamics, it's very time consuming. So my experience is a smaller population in genetic algorithms, but the longer computation. So if you, for example, you may assume that 200 fitness function evaluation. So maybe it's better 10 population, 20 generation, yeah?
Yeah.
It's my experience.
Yeah. And the number of decision variables?
So to the coding the task. So you have to think how to code the task.
Yeah.
This is important. I didn't mention about it. When you choose the design variables, it's better before optimization to check perform some sensitivity analysis.
Okay.
You check how this design variable is sensitive on the objective functions and may get rid of some of them. If you reduce the number of design variables,
yeah, we have been using optimization.
Not for every case. I don't remember. Yeah, but we sometimes we.
That's what we try. We have been using optimization for groundwater problems, but there we have like maybe 2,000-3,000 nodes at least. So, and maybe you have more than 20 or 100 decision variables.
It's very large value. So you have to think about model reduction.
Yeah, but you know,
sometimes it's impossible. Yeah.
Yeah.
It's an open question. I don't know how to answer it.
And between genetic algorithms and neural networks, what do you prefer?
This is different because neural networks is not used for optimization. Neural networks is some kind of approximation. Sometimes we use it. You may use it for example, to omit the numerical simulation. That was a PhD in our department as well. When you trained more or less, you trained the net and the input nodes have a response of the output. Yeah. So you don't have to use the numerical simulation.
Yeah, exactly.
So the net works very fast, and after that you may use it for optimization.
Yeah.
So, but comparison between genetic algorithm and this is the different tools for different tasks.
Yeah, exactly. We have been using both, but sometimes, yeah. Thank you.
Thank you.
Thank you, sir, for your presentation. I would like to ask you about the cohonens method.
Yes.
Is it applicable to a problem that is a non-linear integer problem? Optimization problems such as per se the minimization of standard error in the sample preparation of a chemical reaction which is non-linear?
I cannot answer this question because I don't know how is non-linear in chemical reaction. But again, this is not the cohonens network is not a tool for optimization. This is a tool for the colorful maps inform you how what is the distance between solutions. So sometimes it's used for classification. So I propose you read some papers on cohonens networks. The applications are classification but not exactly optimization. Okay.
Okay. Thank you.
Like this question, we use this for after optimization. After optimization, we have a set of solutions, and we have a problem. We have high dimensionality. So we train this net to make these colorful maps, and after that make a decision.
Okay.
So for non-linear chemical reaction, we don't know. Try to search for articles or papers. To the application of cohonens in your area.
Okay, thank you very much, sir.
Any more questions from the audience? Okay. Can I ask a question as well? Thank you. So, in your last example, you had 6 objective functions, and then you started putting the thresholds in 3 of them, right? And then you checked the area that resulted against the other three. Is there any reason why you prioritized those three?
No, this is the only example.
This is only
You
example.
may start from arbitrarily chosen. I started from the stress.
Exactly, yeah.
But you may start from other. The question is, you obtain the same?
Of course. You cannot, yeah, of course.
But what is the better way? The better way is scatter plot matrix is useful.
Yeah, useless.
No, scatter plot matrix not, but the polar plot matrix. Scatter plot, but it's difficult because you have plenty of and comparing. But this is maybe the good idea is to start with this criterion, make some assumption, solve, choose the region of the optimal solution, and again repeat this process again, starting from a different criterion and see what you obtain. Maybe there is not. This is example. This is not a precise recipe how to choose.
I understand. The way that I see it is that, for example, in a chemical engineering oriented example, that could be there might be some prioritization, saying that safety comes first, so you might want to go there, and then the other objectives might not have a clear priority, which is exactly what you're telling me. Great. And the second question is the following. I think that all the students here, all the people here actually understand completely what is a local and a global minimum when it comes to a single objective function, right? Because a local minimum means that in the neighbor of a point, this point is the best, right? But when it comes to a Pareto curve, we can visually see, you showed us visually what a local minimum is, but I'm not quite sure what it means mathematically to have a local minimum area in the Pareto curve. You see what I'm saying? So the local minima on a single objective means that the neighborhood, it's the best point in a neighborhood, correct? Right. And the global minimum means that it's the best point throughout the domain, right? But how do you classify a certain area, a certain range of the Pareto as local? You see what I'm saying?
For the mathematical benchmarks,
yeah,
you know where is the true Pareto plot.
Sure.
So you may.
Okay.
Yeah, but
gotcha.
For engineering problems.
Gotcha. Okay.
So first we tested. So, sometimes the first metric, the closeness to the true Pareto problem, it is only possible for the test benchmark problems. It's not possible for real problem.
I understand. No. That answers my question excellently. Okay, thank you very much. Any other questions? Okay, so let's thank our speaker one last time.
Yeah.
Thank you very much for your very interesting presentation. Thanks again. Thank you. And thank you everyone online for attending. I will now stop sharing the screen and stop transmitting. Thank you so much. Thanks.